Hi everyone. Today we are delighted to have Nisheeth Vishnoi, who is going to speak to us about convergent and private algorithms for non-convex, non-concave min-max optimization. Nisheeth is a professor of computer science and co-founder of the Computation and Society Initiative at Yale University. His research focuses on foundational problems in computer science, machine learning, and optimization. He is broadly interested in understanding and addressing some of the key questions that arise in nature and society from a computational viewpoint. Here, his current focus is on natural algorithms, emergence of intelligence, and algorithmic fairness. He was the recipient of the Best Paper Award at Fox 2005, IBM Research Pat Goldberg Memorial Award in 2006, and Indian National Science Academy Young Scientist Award in 2011, the IIT Bombay Young Alumni Achievers Award in 2016, and the Best Technical Paper Award at ACM FatStar in 2019. He was elected as ACM Fellow in 2019. He also has a BTech in Computer Science and Engineering from IIT Bombay and a PhD in Algorithmic Combinatorics and Optimization for Georgia Tech. It's a pleasure to have you, Nisheeth.
Thank you so much. Thank you, everyone, for logging in. Thanks, Abhadeep, for the introduction and also the invitation. So I changed the title a little bit. It is to just kind of focus on the modeling aspects of what I'm going to talk about, and also give you a little bit about algorithms. So the title of today's talk is Efficient Alternatives to Min-Max Models. And let's start with the basic setup, which I guess everyone here knows, but I just want to kind of recap quickly. So the connection between learning and optimization or minimization. So you have an agent who's trying to learn from data, and one of the prominent approaches to do that is the following: that you convert your machine learning problem, which includes data, by picking some model and reduce it to optimizing some kind of a function f, which searches over the parameter space of the model. So this, I guess, is not at all news to anybody here. And in the real world, as all of you experience on a daily basis, the data sets are very large, and hence the functions that we are talking about are becoming increasingly complex and high dimensional. And this gives rise to optimization problems over very interesting landscapes, not convex, highly non-convex in most cases. And one of the questions that arises is that, since in general, finding global solutions to non-convex problems is hard, what do we do? And one of the solution concepts that has emerged in this area is to use local solution concepts. So things like, as you can see in this picture here, I have inverted it because that's, so if you see the difference between the figure on the left and the figure on the right, is that the figure on the right is a 180-degree rotation of the figure on the left, because we're minimizing, so we want to go as down as possible. So we want to find the function value of minimum. Anyway, so that's, if you didn't get it, it's fine. It doesn't really matter. This is all just a cartoon at this point. So there are many possible places where you could go. Not all of them are of minimum value, but there are these local optima, and there have been recently, in the last few years, study of efficient local minimization, and it is a reasonable theory at this point and also useful. But that's not the focus of the talk. The focus of the talk is robust learning, which is a very broad term. I guess I'm not using it in any specific context at this moment or in this entire talk. One problem with the learning setup that we talked about in the previous slide was that during the actual learning, it's possible that there's interference of various kinds. So for instance, data that we are learning from could be noisy. For instance, this could be because maybe the data has some privacy guarantees, or it needs to have some privacy guarantees. It could be altered or could encode societal biases, for instance, and that can also be viewed as some kind of noise. But besides noise, there could be also active attempts to change the data through what are called adversarial attacks, data poisoning, and so on and so forth. And yeah, so things like that. So one of the things, one of the approaches, and I say one of the approaches because there are many, many different ways to do this. One of the approaches to handle this kind of noisy or adversarial learning problem is to appeal to the model of min-max optimization. So at a very high level, this corresponds to, okay, there's some issue with the, yeah, so there's some issue with the thing, but so at a very high level, this corresponds to splitting up the optimization problem into two parts. So there are these x variables, which are the variables of the model that the learner would like to know. And then there are these y variables, which are controlled by this adversary, which is in red. And the adversary could be using, could be either perturbing the data or any other thing for that matter. And so if you do not know much about what the adversary can do and cannot do, then one way to formulate the new optimization problem is the learner's goal is still the same, to minimize over the model parameters, but the adversary's goal is to fool the learner. So it searches in the space of its allowed perturbations or noise or whatever it is, the best way to fool. So it's a maximization problem. Because the adversary knows that the learner is minimizing, its goal is to maximize the function. And this gives rise to this min-max optimization. This is a beautiful formulation, very long history. It comes from at least 70, 80, 90 years. Von Neumann was one of the first people who used min-max optimization. And it has been prominently used in, these model has been prominently used in economics, game theory, optimization, and more recently in machine learning. In particular, the original paper of Goodfellow and others who introduced GANs appealed to this for unsupervised learning. And also more recently, papers by various researchers working in robust learning use a min-max formulation to learn in the presence of adversarial attacks. So I guess this is all common knowledge. Oops. Yeah. So since I mentioned von Neumann, I mean, one thing to note is that von Neumann was looking at very simple functions, essentially bilinear functions. And that's a special class of, that's a special case of convex and concave setting. So when I say convex concave, I mean that the function f is convex in x and concave in y. And this is reasonably well understood, as you can imagine. Just like convex optimization is reasonably well understood, convex concave setting is reasonably well understood. But in machine learning applications of the kind I mentioned, f is non-convex in both x. Well, it's non-convex in x and non-concave in y. So the question that arises is, can we develop algorithms to solve this model? And as you may already notice, that global optimization is out of the question, because a special case of this is when there is no y, when there is no adversary, and global minimization is not what we are looking for. But what we are looking for is some kind of local convergence or local optimization notions. So this is really the bottleneck, and this is the frontier of this whole area. Can we find locally convergent algorithms from min-max models where it is not at all clear what it means to be locally convergent? Okay, just to point that out. So this is, in my view, machine learning optimization 2.0, and I guess given the generality of this model, it is important to either understand when we can optimize this model locally or come up with alternatives for this model, which equally capture the problem that we started off with, of learning in the presence of adversaries. So in this talk, I'm going to focus on, or at least use the example of unsupervised learning, which was also cast as a min-max optimization problem by in this paper of Goodfellow and others. And do I need to go into details of this, or I guess it's not particularly important to know precisely what's happening. But roughly speaking, this is in this setting, there is a generator whose parameters are encoded by these set of variables x, and there is a discriminator whose parameters are encoded by this set of variables y. And the goal of the generator is to take random noise and convert it into images which look like, in this particular case, let's say the MNIST dataset. And the goal of the discriminator, which has some samples from this MNIST dataset, is to catch the generator and keep punishing it unless it actually starts giving out samples from the target distribution. So it's not obvious that this is a good framework to do unsupervised learning. This is a play on the variational autoencoders and other related methods that were proposed. But this is a neat model, and it gives rise to, once I plug in a specific loss function, which in this case is a cross entropy function, it gives rise to an optimization problem, which is over variables x and y, and parameterized by the data set, and also the random noise which the generator starts with. So the problem that Goodfellow and others wanted to solve is min over x, max over y, f of xy for such an f of xy. Any questions? I mean, please feel free to ask questions in this talk, since this is a pretty informal thing. Okay, so let's keep moving. So let's talk a little bit about what's going on in this world of min-max and why things are a little bit more tricky. So first of all, let me just say that there is now a pretty wide body of literature which is trying to characterize and understand these so-called local minima or local saddle points. And very roughly speaking, these are points where x and y, where y is a local maximum of some kind for the function f of x, where we optimize over this dot here. I don't know if you can see my cursor, but yeah, you can. And x is some local minimum of this function f of y, where we optimize over the first set of variables. And it's not really important right now to understand what is the notion of local minima that we're talking about. But there are various notions of local minima that you can already think of. So in this yellow box that you see right next to it, for a function L, I just use a different symbol because I want to separate out the L and F. So L is just a function of X, and you could say that a point X is a local minimum of L if the gradient at that point is small. That's some kind of first order local minimality condition. And similarly, you could say, you could give a second order definition where point X is a local minimum if the gradient is small and the Hessian is, well, ideally it should be positive, but it is not too negative. Okay. And for the maximum, you just have to flip the signs. So since maximum and minimum are related by signs, you can take these definitions of local minima and convert them into definitions of local maxima. Okay, so the problem is that unlike just the minimization setup, there are very simple examples where such points do not exist. And even when they do exist, there are kind of complexity theoretic results, if you care about them, which show that they are hard to find. Okay, so this is this seems like not the right way to go in general, but the importance of this model is such that people have been still trying and they've not given up. The key issue, in my view, is that these agents, either the learning agent or the adversary who can only make local predictions, are unable to predict their opponent's responses. And this leads to convergence problems in algorithms, which are actually being used. So you may ask what algorithms people are using for this. And one very simple algorithm is the gradient descent ascent, where you do a descent step for the minimizer in X, and you do an ascent step for the maximizer. Okay, this is a very simple algorithm which you can use. Nobody's going to stop you from using it. And there are variants of it which include momentum and other things called optimistic mirror descent and so on. But the problem is that all of them eventually cycle because of some vague intuition that I have written down. So if it makes sense, it's fine. Otherwise, maybe just look at these pictures here. So this is really what keeps happening in these when you try to use GDA type algorithms to learn. So you have in front of you two examples. One is trying to learn a mixture of 4 Gaussians. And on the right-hand side, you have an algorithm which is trying to learn the 0-1 MNIST data set. So there are only two digits, 0 or 1. And what you're seeing is that the algorithm like GDA, yeah, it converges. It figures out one mode. So by a mode, I mean, so in both of these data sets, there are modes. In the first, on the left-hand side, in the Gaussian case, there are 4 modes corresponding to the 4 centers of the 4 Gaussian. And in the 0-1 MNIST, there are 2 modes corresponding to 0 digits and 1 digits. So it does learn 0-1, but it forgets. Once it learns 0, it forgets 1, and when it learns 1, it forgets 0, and so you keep cycling. And that is exactly what this point is trying to address, because they're only able to see to estimate what you're going to do in the next step, and they don't have a long-term view on your strategy. They keep chasing each other's tail, and cycling happens. So it's really important to actually, in this, not forget that we cannot really we cannot really hope for convergence unless somehow we enable the players to when they are trying to estimate what they should do, to let their opponent move as much as they can. If you only let your opponent take one step, then maybe and you take one step, but if both of them know, then you can already see that you can try to figure out fooling strategies, which is what is happening here. So I'm going to mention our results first at a high level, and then maybe tell you a little bit more details. So our main contribution is, so these are joint works with Oren Mangubi, who's my postdoc, and Sushant Sachdeva from Toronto. So there are two papers. The purple one is the second order one, and the black one is the first order one. So there are two papers which give two different notions of, or two different alternatives to min-max. We call them, loosely speaking, epsilon greedy min-max. And I will explain what this is. And in this, with this notion, or with this alternative model, the problem of finding a point where the algorithm stabilizes or converges to becomes polynomial time. Okay, under some very weak assumptions on the function, like it's bounded and it's Lipschitzian. So in particular, we do not need any assumptions on the starting point that you need to start close to something. We do not need any convexity, concavity, or monotonicity as prior works have assumed, which have tried to come up with efficient algorithms for min-max optimization. The key idea is in this, already hinted about. It's in this notion of defining a new equilibrium concept by essentially placing computational restrictions on this adversary. So there were two extremes. When we started looking at this work, there were two extremes. One was where you say, okay, you let the adversary do whatever it feels like. So if the adversary sees that there is a point somewhere there where if it jumps and it can increase its objective function significantly, we have to take that into account. But in practical implementations like GDA and its variants, you are just trying to estimate what this person will do in one step in a very small neighborhood around the point. So there's this huge gap between these two strategies. The hardness comes because you let the adversary do whatever it wants to do. And the cycling comes because each one is just looking at, one step of the other.
So Nisheeth, one question I had with this intuition is that this kind of a formulation is used in, not in this min-max settings, but in this this kind of alternating minimization settings, right? In alternating minimization, when you alternate between the minimization in each of the variables, you don't take a small step, you actually minimize that function.
That's correct. Yes. So if you could do that, so if the function is bilinear or something like that, you could do that. Or if the function is convex concave, right, then you could do that, because and then you can do it actually. The problem is that because if you are at a point, you do not know, there may be many local minima to which this adversary can go to actually, or local maxima to which this adversary can go to. So which one will it go to? You don't know that. Right? And that is the key technical issue, and I'm going to come to that in the next slide.
Perfect.
Okay, so I just want to point out, make one or two more remarks. That the first is that this first order algorithm is super practical. In fact, its time and memory complexity is the same as GDA. And the GANs that we use to train them seem pretty stable. And we're also working on this adversarial learning setting. And I guess, yeah, it's always interesting to hear your thoughts at the end about what potential other applications we could imagine. Okay, so let me try to introduce this this concept of a greedy path. So I'm introducing this for the first order setting. The second order setting is just a bit more complicated, but technically we did it for the second order setting first, and then we did it for the first order setting. So the key computational restriction that we apply on the Y player or the Y adversary is the following: that it can go from its current point to any point as far as it can be. The condition is that its the function f should be increasing at a particular rate on this path. Okay, so in that sense, it's greedy. And the reason why we did that is because we said, okay, at least in some settings like GANs, or when you're trying to find adversarial attacks, you're not going to be using magical algorithms to find these attacks or to you know or to yeah, you're not going to find magical algorithms. You will have to work with the current algorithms, and the current algorithms are things like SGD or GD or Adam or whatever, right? I mean, and all of these fit in our framework. So the Y player could be using any of these algorithms, and it doesn't have to fix any algorithm in a single algorithm throughout the implementation of our algorithm. It could be choosing different um, uh, paths. So just to give you a sense, pictorially, here you see a point A, and you see this circle region, or this kind of this region that is marked out. This is the set of all points reachable from A, where there is a greedy path that connects A to the point. So in particular, B is a point that you see here you can reach, but C, which is looks like the highest in this region that you see, is not allowed, because to go there, it has to actually suffer a loss before it can start climbing up again. Okay, so this is the model. And this is really, I mean, in some sense, a computational lens on this problem, that why worry about adversaries which we are not going to encounter in certain contexts. And then we define a new function, which is the supremum. So this is a function. So you are at a point x comma y, and you start changing y, and you start at y, and you follow some greedy path, and you reach w. And so you define this function g sub x of y, and yeah, you could also do this for the case when there is a second second order condition. And these greedy paths model first order and second order optimization algorithms respectively. That's really the motivation for us. And the conditions are similar to what I mentioned before. So there is a subtle change here now. So in the standard min-max optimization problem, you would want a point x star y star where the gradient of f with respect to y at the point x star y star is small, and the gradient of f with respect to x at x star y star is also small. But in our model, the second condition is changed to the gradient of this greedy function with respect to x at the point x star y star is small. Okay. You have any questions?
Yeah, I think I missed the definition of the greedy path. When you take the soup over greedy paths, what are the greedy paths?
So greedy paths are any paths. So for example, in this picture, the path from A to B is a greedy path. So greedy paths are paths which you can take where you start at some point, it could be any point, and you move until the point where you can no longer increase the value of the function.
I see.
And you call that point W. So that's where this W is coming from.
I see. And
so this is the end point of a greedy path y comma W.
I see.
And there are infinitely many such paths that you can imagine. So we'll come to that. This is a pretty nasty function, this g of xy.
I think there is a question on the chat.
During the greedy path, is x fixed? It's fixed. X is fixed. Y is also fixed because that's the point where you were, but you're only changing the y coordinates. Okay. No. Okay, so yeah, so it's x is fixed. Yeah, that's right. So y player, because y player cannot change x. So that's the way to think about it. Does that answer your question? I mean, I can only change my variables. The discriminator cannot go and change the generator's variables. So it doesn't make sense to define a path in which you can also change x. Is that make sense? Okay, great. And the second order definition is just a bit more complicated, but it's also motivated from a local definition of second order min equilibrium, which was proposed by Nesterov and Polyak in 2006. And note that again here, while for the y, the difference between w and y, I mean, I see a question here, so I'm just responding to it. The difference between w and y, and this is important, is that because okay, so you are starting at y and you're changing y and you reach w. So what I should have really written is, maybe I'll just make that edit right away. Greedy paths from y to w. Okay, so you're basically changing over. You fix y, you take one greedy path, which takes you to w. So the supremum is really over w in some sense. Is that clear?
Hey, so are you essentially kind of flattening the top of the like the optimization surface? Like if you think of it as hills and valleys, are you kind of flattening the hills a lot more on the top?
No. What makes you think that? I'm just curious.
Because g of xy is kind of a supremum of all. G of xy goes to the, like if you have a y which is close to a hill, it's g of xy will be the f of xw on top of the hill, right?
That's right.
So you're essentially mapping.
Here you can see in this picture there are 4 hills surrounding the point A, right?
Yes.
So wherever is the largest value, so maybe here the value on one hill is 3, and one hill is 2, and one hill is 1, and so on. That's what you will associate to this path, to this point A. So just a maximum or supremum over all these paths. So I'm not sure I'm flattening the thing, but maybe there is a way to see that like that. But we are not trying to flatten the function. It is just saying that, okay, we allow the y player to be greedy, and that's the only restriction we have on the y player. We do not restrict how far it can go.
Got it. Thank you.
So as long as you're gaining by moving, you keep moving. I mean, you can imagine that people are driven by such motives, right? I mean, you keep moving in the space, of companies from Google to Facebook to Apple, as long as the salary is increasing, right? Or do you, maybe you do sometimes take a salary hit and then you move to a better position or a better company. I don't know. I'm just joking. But this is not a totally unimaginable thing, and I think more importantly, it models the classes of first and second order optimization algorithm.
Thanks. Okay.
So this is these are the 2 definitions of equilibria.
Actually, one question I had before moving forward. So when we talk about this, like the greedy strategy for the adversary, how does this capture things like momentum? Suppose I reach the maximum, I can still go up slightly farther, I can go down. Right? Some optimizers which take momentum into account. How does this capture momentum?
So that's why we have this little epsilon here.
I see.
So, I mean, I'm not at all being precise. I mean, these papers are actually pretty complicated once I start writing the whole math here.
Right.
So yeah, so you're right that we have to take into account a little bit of fluctuations.
Okay.
Yeah. So yeah, I think the key take home from this slide is that when we try to model adversaries in machine learning algorithm, we need to think carefully what we're doing and whether it is really an adversary, because that can make your problem computationally very hard. It's not like this. I mean, once I define this, it's any easier. It becomes very easy, but still there's hope that if you start thinking about the adversary in an interesting manner and more realistic manner, you might have some hope to come up with really good algorithms. So there is still hope for min-max optimization, or at least min-max type optimization. So the question that actually arises once you start thinking about this is this function g differentiable? I mean, what am I saying here? I mean, I'm talking about the gradient, but is it even differentiable? And if it is, how do I evaluate or access it? Because this looks like a pretty messy function. It's a supremum over infinitely many paths. How do I evaluate it? Right? I mean, in the previous case, it was easy because it was just f. So you can take the gradient of f with respect to x or y. Now you're taking the gradient of this g with respect to x. So how do I evaluate all this stuff? This is not a trivial thing at all, actually. And in fact, the bad news is that this function g can be discontinuous. There are examples, easy examples that you can construct. And that's because if you perturb the point a little bit, you could go from the path, the maximum path could be to the one valley, I mean, to the one hill as opposed to the other hill. So there creates this, it creates the discontinuities very easily. So one idea is to replace this function by some kind of a smoothing. Okay, I'm not going to explain any of these details, but there is a precise sense in which I can smoothen the function. And but even if, so let's assume that it is differentiable. Okay, even if it is differentiable, which hypothetically I can, let's assume, computing the value of g may be difficult because g is the supremum over so many paths. How are you going to do that? And the idea for us is that instead of thinking of this as the supremum of many paths, it turns out that our analysis works if we pick one carefully chosen path, one carefully chosen greedy path. And so we don't have to compute this supremum over all possible paths. That's one interesting technical thing. I'm not sure I'll be able to explain this. So the first order algorithm looks something like this. It starts at a point xy. It updates y by computing gradient descent. So here's an example of how we pick just one greedy path. Okay, so we fix gradient descent as an algorithm. So we start at x comma y. We keep updating y by doing gradient descent until we reach a point w where the gradient is close to 0. Okay, and then we let this function h at x comma y to be equal to f at x comma w. And if you want to minimize this function h for this, then you need to move in the direction of negative gradient of h. And this is a similar problem. Computing the gradient of h may be very slow, even when it's differentiable. So here comes a new idea, which is actually comes from the realization that as far as h is concerned, we really can only assume we have access to the value of h, which means that we have a 0 order oracle for h. Okay, and we would like to do optimization of this function h with respect when we have 0 order oracle. And here we kind of borrow an idea, which is an old idea. I think I first saw it in the paper of Abraham Flaxman, Adam Kalai, and Brendan McMahon, who I saw pop in here, which is you will see manifest in here. So how do you do gradient descent without computing the gradient? And so one idea is to kind of try to move in a random direction so that your expectation is the right one, and you update x in a random direction like a Gaussian, and accept only if it causes the value of h to decrease. The problem with this is that this random Gaussian vector that you're picking will be almost orthogonal to the steepest direction. So there is a specific direction, which is the gradient of h at x, in which you'd like to move. You just have no way to compute it. So if you pick a random Gaussian, there is a very small probability that you will actually, there's a very small projection of this vector along this direction that you would like to move. But this doesn't seem like a particularly practical strategy. And so what we do is something semi-interesting, or even more than semi-interesting, I would say, that we propose an update step in the direction of the gradient of f itself, and let the discriminator update using gradient descent.
So Nisheeth, to kind of make the idea one work better, can't we do something like what the follow-up paper to Brandon's paper, this paper by Alek Agarwal, Offer Dekel, and Lin Jiao? What they did is, like, instead of taking one single point, it is like one-shot gradient you are finding, right? Evaluate d such points if it is in a d-dimensional space, and that reduces the variance of the grade estimator much lower.
Yeah, that can be tried. What I'm going to show you is, yeah, but that's an interesting idea. I think we should talk about it, the technicalities of it, maybe offline.
Sounds good.
Yeah. So what I'm going to show you, I don't know how much time I should spend. Maybe I should wrap up soon, right, Abhijit, because I want to take some questions.
Definitely.
Okay. So I can go into a lot of detail about this algorithm, but let me just show you this one slide quickly, or at least flash it, and then you have the talk recorded. You can also read it. So one idea that we do in our first order algorithm is the following, that we propose an update in the direction of the negative gradient of f with respect to x. And let y do gradient descent. I think there's a typo there. It should be gradient descent. And the reason, and so why is this a reasonable thing to do? And this is kind of the core essential argument as to why this is something even worth doing. So if the x player proposes an update v to x, the y player updates, because it's greedy, it will go to a point where the value of f is higher. So in particular, h of x plus v, h at x plus v comma y is at least f of x plus v comma y. And the hope is that this is not just a greater than equal to, it's significantly more than that. And since y is a first order equilibrium or stationary point, we also have that h at x comma y is the same at f of x comma y. Okay, because you started off at a first order equilibrium. So you see, we assume that our starting point was already the end point of some greedy path. So we are using that here. It's a slightly subtle point. I can come back to this if there is real interest in understanding that. But combining these two things, we get the following inequality. And these two inequalities along with the equality suggest that the direction to move is the negative gradient of f with respect to x. Okay, and here is a little bit more explanation of this. Yeah, and what we really end up doing in our first order algorithm, which we apply to GANs, is we actually do a batch gradient, which is somewhat similar to what Abhijit is suggesting, but not quite. Okay, so there are some other details in the algorithm, but really this is how it ends up looking. It's the first order algorithm is really surprisingly simple, as you can see. The proof is not, but the algorithm ends up being pretty simple. Okay, so how does it perform in practice? So you can see some figures here. This is the classic example people use to understand convergence of these methods. So on the left, you see, so this is the function f of xy is just equal to xy, which is a bilinear form. And on the left, you see this gradient descent, which is non-convergent from all initial points. And on the right, you see our algorithm. You can read more about this stuff in our paper. But so for this very, very simple toy case, it works. What about for these more interesting applications of GANs? And here we observe that, as you can see in these images, on the right-hand side of this line, that our algorithm actually seems to learn all modes in most of the experimental runs. So it's doing something useful. It's certainly very fast, and it seems to be improving the situation when compared to GDA and other such algorithms. Okay. Yeah, I don't want to focus too much on GANs because I started this talk off by saying that there are possible alternatives to min-max optimization, but this one is a particular application, which is this paper with Sushant Sachdeva and Nonconvex-Nonconcave. Okay, I'll just conclude now. So the main contribution of this work is conceptual, which is to give alternatives to min-max optimization and give computational feasibility to many of these robust learning problems, as long as you can imagine that the adversary is restricted to being a greedy adversary. And that's really the key idea, to constrain the discriminator or the adversary or the Y player to greedy optimal strategies as opposed to any strategy. For more technical people in the audience, the second order equilibrium notion that we propose, or the second order equilibrium, min-max equilibrium that we propose, actually generalizes that of Nesterov-Polyak, and in fact can be viewed as a zero order variant of the result, in the sense that how to do Nesterov-Polyak, which is local minimization in the presence of just a zero order oracle to the function. Our algorithm is polynomial time, and it's highly memory efficient, even though it seems to be looking up forward, but because of randomness, it doesn't need to keep track of all the paths. It samples one random path, and that's, the theoretical guarantees are good, but not great. I'm sure that they can be improved, and that's something for the future. And I guess doing some current work on trying to understand robust learning and how our algorithm does in that setting. And in that process, we have discovered issues with existing algorithms for robust learning, which is very interesting. If you want to read more about these two papers that I talk about, I have this blog post with Sanjeev Arora called Off the Convex Path, and a couple of months ago, we posted blog post for these two papers. And I think I'll stop and take questions. Thank you so much.
Thank you, Nisheeth, for the talk. This was really exciting and enlightening. I was just wondering if anyone in the audience has any questions. If not, then I have a question for Nisheeth, and in relation to, I see Nicholas in the call, Nicholas Carlini, who works on adversarial examples from a completely practical standpoint. I was just wondering, Nicholas, do you have any thoughts on this direction of work, which is very much theoretically motivated in comparison to something which is done practically?
I was only here for the second half, so I don't know if I have anything that I want to sort of go on the record as saying.
I think there is a connection, which is, so there is a work of, I don't remember all the authors, but Alexander Madry and his co-authors proposed an algorithm to do robust learning. I think this was one of their first papers on this topic. And essentially, what we are showing is that that's a reasonable thing to do. So in their algorithm, the way they are learning is by, if I remember correctly, and Nicholas or others can correct me, is that the person, the agent which is trying to look for adversarial attacks is really using some kind of a greedy strategy in a box to see if there are perturbations within a small box which will increase the loss function of the learner. So I don't think they have any guarantees associated to their work because, okay, so one obvious problem with any of these things in general machine learning, non-convex optimization is that there is no way to kind of relate where you converge locally to what you want to converge to globally. I mean, there is no guarantee as to wherever we are converging is actually a good point. But that's a more universal problem. But assuming that all locally convergent points are reasonable or have some information about the distribution that you're trying to learn or the classifier that you're trying to learn, this is a reasonable thing to do.
I see. So on that line, one question is like, if you reach this local minimas, you said like there are practically people use this GDA style approaches, and this is another approach of doing this. So do you have a sense of how noise robust will these two approaches would be?
Well, GDA doesn't converge even for very simple examples. So, and I guess what you're talking about is, so we can allow stochastic adversaries as well. I didn't mention this. In the following sense, that the definition of greedy path that I mentioned in the talk really is a cartoon, because it says that your payoff should increase at every time step, right? And it's a deterministic strategy, but you can extend this to stochastic paths where in expectation you're increasing.
Oh, I see. That's what I was basically asking. Like,
Yeah.
how are these things noise robust?
Yeah. But things become very delicate mathematically.
I see. Any other questions from the audience? Yes, then. Yes, and then I guess we should thank Nisheeth again for this amazing talk. This was, now I think I understand min-max optimization much better, at least now. Thank you, Nisheeth.
Well, thank you, Abhijit. Thank you, everybody.
Thank you so much.
Have a great day.